Welcome back, students. This is the session 9 from the playlist of circular motion. The topic is the motion of a vehicle on a banked road. So this is a figure which I have drawn here in order to explain this topic. So here there is a vehicle which is moving on a banked road. So this is the banked road, that is OA is the surface of the road, and this road has been taken as frictionless in this session. So this road is frictionless, and this road is banked at an angle theta with the horizontal. And here this OB is the width of the road and AB is the height of the outer edge of the road. This can be taken, let us say, if B is the width of the road and this H, let us say H is equal to the height of the outer edge of the road, and this road, that is OA, this is banked with the horizontal at an angle theta. Now when the curved roads or the circular roads, they are banked at a certain angle in order to prevent the skidding of the vehicle. So from this figure we can see that the weight of this vehicle will be acting vertically downward. However, this surface OA, this will be exerting a normal reaction which will be perpendicular to this surface. So this is the normal reaction. Now this angle, this banking angle is theta, so this angle will also be theta, and this component. So what I have done is I have resolved this reaction R into two components. The vertical component is equal to R cos theta, and this horizontal component is equal to R sin theta. Now in order to prevent the skidding of the vehicle on the circular path, or you can say the curved path, this R sin theta should be able to balance the centrifugal force which this vehicle is experiencing during its motion in a curved path, and this R cos theta will balance the weight of the vehicle. So this is let us say the equation number 1, this is the equation number 2. Now if I divide these two equations, what I will get is that is R sin theta divided by R cos theta will be equal to tan theta, and this tan theta will be equal to mv square by R divided by mg. So this m and m will get cancelled out, and finally I will be left with v as v square upon rg. So it implies that v square is equal to tan theta into rg, or we can simply say that the speed of the vehicle on this banked road will be equal to under root of rg tan theta. Now this equation is valid when the road is frictionless. For the road to if the road is frictionless, then this formula will be different, and we will be deriving that formula in the next session. So this formula is valid only when the road is frictionless. Now if the width of this road is B, here I have taken the width of the road as B, and the height of the outer edge of the road as H. This AB is equal to H, and OB is the width of the road which is equal to B, and AB is the height of the outer edge of the road. So in that case we can also write this equation as V is equal to under root R G tan theta, and this will be equal to H upon B. So with the help of this formula we can calculate the width of the road, or you can also calculate the height of the outer edge of the road if the other parameters are given to us. That is, if we know the radius of the this circular path, if we know the banking angle, and if we know any one of these if we know any one of these two parameters, then we will be able to find the other one. So this is an important formula, that is V is equal to Rg under root Rg tan theta, and this is equal to H upon B. So thank you very much for joining this session. In the next session number 10, I will be discussing about the motion of a vehicle on a banked road, but in the next session we will be considering the road to be having some friction. So means the road will be rough in nature. So thank you very much for joining this session, and till then have a nice day. Bye.